Good morning, one and all. I am Dr. Ramya Swetha, Assistant Professor, Department of Civil Engineering from Institute of Aeronautical Engineering. Today, our topic is absolute maximum bending moment diagram, and in the part of analysis of structures. So, under what are the various types of arches, how we are understanding the arches, what are the various types are involved according to their hinges types. So how three-hinged arches are working, these are all we will see in our previous classes. In this particular class, what we are understanding in this lecture, what we are understanding is the absolute maximum bending moment diagram. What are the steps we follow for this and how we are understanding this for the arches. So in arches, how we are understanding this parameter, that is absolute bending moment diagram. So here in this, first understand the structure. So consider it is a three-hinged arch. We know three-hinged arch is nothing but it has two hinges at a starting point and ending point of the arch. Whether those are having the same point, those starting and ending point are at the same axis, it may or may not be the same axis, and one more at the crown. So it is independent of the whether it is parabolic shape, circular shape, whatever it may be. So whenever we have three different hinges, one hinge at end, other end at starting, and one more at this crown place, such type is known as three-hinged arch. And in this, two hinges at supports and one hinge at crown. So it is statically determinate structure. It is a statically determinate structure. It means the equilibrium equations are enough for know about the unknowns in this particular three-hinged arches. So here, based on that, here it is without needing these compactability conditions. And similarly, what is meant by this static equilibrium equations means, so all the sum of the vertical forces which are involved in the three-hinged arches, so involved whether it is uniformly distributed load, fully uniformly distributed, or any point loads are acting. So the sum of all vertical forces, that is equal to sigma f of y is equal to 0. This is the one of the equilibrium condition. As similar these vertical forces, horizontal forces which are involved in this any kind of arch, so that total sum of the horizontal force is equal to 0, and movements involved in that particular condition of the arches, so sum of the movements is equal to 0. These are the conditions which we are consider for this static equilibrium conditions. So these three equations are enough for finding the unknowns in this arch, three-hinged arch, such type, that is nothing but the statically determinate. So here we have to understand these are the conditions will help us calculate the reaction forces at supports A and B. So these are the things which we are going to understand as per the given data. And so how we are going to understand these reaction forces, how we are going to do the further steps for finding these horizontal reactions and these absolute bending moments, all the parameters. For simplicity, for simplifying this, let us assume uniformly distributed load. So that is nothing but W is our uniformly distributed load applied across the span. So how much span? So there is a difference between the length of the span and the length of the arch. So the span between the 2 points, that is starting and ending, this is nothing but the span of the arch. Span of the arch, and this completely from starting to ending, this complete is nothing but the length of the arch. Length of the arch is span of the arch. Both are two different parameters which we have to understand in arches. So here, so whenever we are applying across the span of the arch, we need to calculate the reactions. Those reactions are vertical reactions at supports from starting point and ending point. We may consider A and B are the starting and end supports respectively. So here we have to understand the vertical reactions at supports both A and B, and also the horizontal reactions due to the based on the arch shape and the hinge at the crown, because we consider this is a three-hinged arch here. So we have to understand the horizontal reactions due to the arch shape. It depends upon the shape of the arch, whether it is maybe parabolic or semicircular. These are all the various parameters which are involved in this arch. So in this, we are using these following steps for identifying the various reactions. So in this, first we have to consider the movement about the one of the supports. For example, consider A to find out the vertical reactions at the support B, and use symmetry or horizontal equilibrium equation to calculate the horizontal thrust at the support. Like this, we are going to understand we are going to find out the reactions. Consider what kind of, whether we are going to consider the uniformly distributed load or uniformly varying distributed load, concentrated loads. So the mix up of all different loads may be considered. So it depends upon the design and where we are going to apply, how it is going to consider all these things, all these characteristics. So these are the parameters in general, but just for simplifying the parameter, simplifying the things for understanding, we are considering here this uniformly distributed load across the span of the arch. So here we are going to calculate these vertical reactions as well as the horizontal reactions, and also some of the moments we are going to consider for identifying the horizontal thrust at the supports. So these are the horizontal thrust. We consider those supports. So now moment at any section. So we consider any section here, here. It depends upon the requirement. We are going to consider at any section of the movement of the arch. So we have reaction forces already we are going to calculate. So now here we are going to calculate the bending moment at any section X. So this is the span of the arch, and in between the small for section, that is nothing but the X distance. So L is the span where we are consider this section, that is nothing but the tilde, that is X. So the bending moment at X section depends upon this bending moment, which is depends upon the both horizontal reactions and vertical reactions. So the distance of the section from the supports and from the crown we are going to understand. So the influence of the load on that section. So the general expression for these bending moment at a section can be derived from the sum up of moments around the point. So consider both vertical and horizontal thrust for finding the moment at any section where we are consider that section for calculating the bending moments. So here the exact word what we are going to understand, that is the absolute maximum bending moment. So the absolute maximum bending moment is the largest value of the bending moment that occurs in the arch under the worst possible load condition. So for uniformly distributed load, this maximum moment will occur at a point between the crown and the supports. So it between the point whenever the crown we are consider from there to these supports. So in this, for example, the maximum bending moment in uniformly distributed case. So for a three-hinged arch with span L, rise H, and uniformly distributed load W, what we consider? So the maximum bending moment is equal to WL square by 8H. So it is simplified case when considering the symmetry and uniformly loading. Already we know about this symmetry and also unsymmetrical conditions. So we may consider n different under different shapes, not only parabola, semicircular, like this different shapes we are going to understand. So according to that, we have to understand these maximum bending moment. In this particular, what we consider, that is, we are going to see this maximum bending moment WL square by 8H. So here we know L is the weight is the load, W is the load, L is equal to length of the span, H is equal to rise. These are all the parameters which are going to involve. So this L is nothing but the span and H is nothing but the rise. This is the weight. It depends. So uniformly distributed load, UDL. So like this, this is the example formula for this maximum moment under UDL, under uniformly distributed load. Under point load, half of the portion having uniformly distributed, remaining the distributed load is different, not only uniformly throughout, and also various point load concentrations are there. So these are all various parameters which are involved for understanding this absolute maximum bending moment. Coming to this, whenever we are consider a semicircular arch, so we have parabolic arches, semicircular arches, each have their own kind of geometric properties and requirements are there. So here a 3-hinged semicircular arch of uniform cross section is loaded as shown in the figure. So here the figure shows, here it is a 3-hinged semicircular arch. So here it is a 3-hinged, it means one hinge at A, one hinge at B, and one at crown C. Now, calculate the location and magnitude of the maximum bending moment in this arch. This is the task. So as per the given figure, so the distance between the starting point and ending point of the arch, span of the arch is equal to 30 meters. That is nothing. This is nothing but the span of the arch. So that is equal to L is equal to 30. And the rise from the where the axis both A and B are there. So this is B, this is A, and this is C. So this is nothing but the rise. So this is nothing but the rise. Here the rise H is equal to 15 meters. And where we are consider this section that is equal to from A to that section that is equal to 8 meters. This is nothing but the X. So here we have to find out the location and where we are going to find out these all the parameters we will see in this particular thing. And this is y-axis and this is x-axis. So these are the things. And how first we have to find out those reactions at A and reactions at B. So this is the given data from this. So we have to understand taking moment of all the forces about hinge B leads to. So that is equal to, once we consider these reactions from hinge 2, so RAY is equal to, reaction is equal to 40 into 22 by 30, that is equal to 29.33 upwards. Because here this is the 40 kilonewtons load is applied from X. From here X is equal to 8, here the load is acting, that is equal to 40 kilonewton. So we are going to calculate. So thus 40 into how much the remaining portion. So from here to here that is equal to, like that we are consider this reaction with respect to Y. And now the reaction at point B is equal to, so we are going to calculate. So total reactions minus RA, that is equal to 40 minus 29.33 is nothing but 10 into 67. Here RA plus RB is equal to 40 is the known thing as per the given data, as per the given figure. What we understand, that is equal to RA plus RB is equal to 40. RA is equal to 40 into 20 by 30. So this is the thing which we are going to understand. Now this is the reaction point of view. Now coming to the bending moment. Now making use the condition that the maximum, that the condition moment at hinge C of all the forces left of the hinge C is 0 is given. So the bending moment at C is equal to 0. It means reaction at A multiplied by 15 minus horizontal reaction is multiplied by 15 minus 40 into 7. So because from here to here that is equal to 30, from here to that is equal to 15. So from here to here this is 7. Because from this is from here to, from A to C that is equal to 15 meter, from C to B that is equal to 15 meter. So from A to this, whenever the load is acting, this is 8 meters, the remaining is 7 meters. So till C. So from this we are going to understand this, the hinge reaction. So reaction minus horizontal is equal to 50 minus 40 into 7, that gives the horizontal reaction. So that is equal to horizontal reaction at A is equal to 10.66 kilonewton. After done all the calculation, we will get this one. Now consider the horizontal equilibrium of arch gives. So now find out this HA. So both are equal. So it is equilibrium condition. It means HA is equal to HB with opposite forces. So now we are consider the horizontal equilibrium of the arch gives. So that is equal to 10.66 kilonewtons. So the maximum positive bending moment occurs below D, and it to be calculated by taking moments of all the forces left of the B about D. So here we have to understand those parameters in this. So now MD is equal to RA into 8 and HA is equal to, here this is nothing but the D. So this is the point. So now we are going to consider the height is given, and there the bending moment is equal to reaction minus horizontal reaction at A multiplied by that height. So this is equal to 93.213 kilonewton is the moment where we required. Now similarly, three-hinged parabolic arch. In previous we understand semicircular arch. So here the three-hinged parabolic arch is, which is shown in figure. Calculate the location and magnitude of the maximum bending moment of the arch. Draw the bending moment diagram. Here also is the same, but here additionally from C to B the uniformly distributed load is acting. Here the uniformly distributed load is acting, and it is a parabolic arch. Length of this span is, it is a parabolic arch. What are the known parameters from these? That is, it is a parabolic arch. And length of the span is equal to 40 meters and rise is equal to 8 meters. And here point load and the uniformly distributed load is acting. So from point load that is equal to 40, the remaining is equal to 10, because from here to here that is equal to 20. So this from here to here, this 20, it is acting 10 kilonewton meter uniformly distributed load. These are the things which we are going to understand in this given data. Now we are going to calculate and understand this parameter. So now taking reactions A as the origin, the equation of the three-hinged parabolic arch is given. So now that is equal to 10x minus 8 by 400 x square. Now RA, reaction at A is equal to, after done by these all calculations, So we will get this 20 into 20 by 2 by 40, that is equal to 80 kilonewton upwards. So f of y. So f of y is equal to RB is equal to 160 kilonewton. The total is equal to, here the distance is equal to 10 and this is equal to 200. So we are understanding this total 160 kilonewtons. Now making use of the condition, the moment hinge C of all the forces left to hinge 0 is equal to 0. Now moment at C is equal to reaction at A multiplied by 20 minus horizontal reaction at A multiplied by 80 minus that left hand side that's uniformly distributed is acting, that is equal to 40 length and this 10 kilonewtons. So finally that is equal to 0. After done all the calculations, so the horizontal reactions at A is equal to 50 kilonewton and consider the horizontal equilibrium of the arches is equal to in equilibrium condition. So HB is equal to 150 kilonewtons. Here the HB is equal to horizontal reaction at B is equal to 150 kilonewtons. Push. And HA is equal to 150 kilonewtons pull. HA is push. This is also from this side. So both the sides it is going to be equilibrium. So now according to the calculus, the necessary condition for extreme, this maximum or minimum. So differentiate with respect to x is equal to 0. So differentiate with respect to x is equal to, we will finally what the location of the bending moment and these maximum bending moment after getting these horizontal and vertical reactions, that is equal to mx is equal to 160 into x minus 8 by 10 x minus 8 by 400 x square. And finally what we will get, that is equal to, so finally that is equal to m of x is equal to 160 into x minus 8 by 10 into x minus 8 by 4000 x square. So here dou m by dou x with respect to the x. So that is equal to 160 minus 8 by 10 minus 8 by 2 by 400. So multiplied by minus by 10x. These are all the parameters which are involved in this. So finally we will get, after done this m of m with respect to x. So differentiate with respect to x this equation. We will get this equation. Finally x is equal to 10 meters. At that particular point, that is the location where we are getting this maximum bending moment. Where we are getting this maximum bending moment. Now substitute the value of x in this particular equation 5. So the maximum bending moment is obtained. So now substitute the equation, that is equal to with respect to x is equal to 10. Finally the maximum bending moment is equal to 200 kilonewton meter. So like this we are understanding this circular arch, semicircular arches as well as the parabolic arches. And this is the shear force at B. The just load we are considering that 40 kilonewton load. So here like this we are understanding this. These are the forces, vertical and all the horizontal. So it makes an angle theta. So this is the reaction, horizontal reaction at A, horizontal reaction at A, vertical reaction at Y, vertical reaction at A. So shear force at D just left 40 kilonewton load. So remaining is not applicable in this particular. Now the slope of the arch which is elevated, tan theta is equal to dy by dx. That is equal to 8 by 10 minus 16 by 400 into x. Now substitute this x is equal to 10. That gives theta. After the calculation we will get this. Theta is equal to 21.8 degrees. Now shear force at D. So here the shear force at D is equal to, so SD is equal to HA sin theta minus horizontal reaction at A with respect to sin theta minus vertical reaction at A cos theta, that gives the finally shear force minus 18.57 kilonewtons. After done these calculations, we will get this one. So this is the shear force at left of the D only. Similarly, where we are understanding this three-hinged parabolic arch of constant cross-section is subjected to uniformly distributed load over a part of its span and is concentrated load of 50 kilonewton. The dimensions of the arch are shown. So evaluate the horizontal thrust as well as the maximum bending moment in the arch. So here it is a parabolic arch. And here one more thing, those two are not having in the same axis. So the starting point and the ending point and the starting point, both A and B of the arch are not on the same axis. So it is not a symmetrical one, it is a unsymmetrical one. So it is unsymmetrical one. The length of the span of the arch is 25. The span of the arch is 25 and this crown is not at the midpoint. So the crown where the C, we consider the third hinged in this. So it is not at the middle point. From here to here, this is equal to 10 meters. From A to C is 10 meters. From C to B is 15 meters and the rise is 3 meters. From A to D, the distance is 5 meters. From D to C is 5 meters. So remaining 15 meters from C to B, uniformly distributed load is acting, that is equal to 10 kilonewton per meter. These are the given things. So here the difference is, here within the same axis, the starting point, ending point are not at the same. So the arch is not a symmetric condition. Now, even though we are following the same steps, here the reactions taking A as the origin, the equation of the parabolic arch, we are going to write like this. X square plus 0.6x. Now taking moments, all the loads about B leads to reaction at A is equal to 1 by 25, 2125 minus 3.75, horizontal reaction at A. So now taking moments of all the forces right of the hinge C, about the hinge C, and sitting moment with respect to C is equal to 0. It leads to reaction at B multiplied by 15 minus 6.7 by horizontal reaction at B minus 10 into 15 by 2 is equal to 0. So the reaction force at B is equal to, so 1 by 15, 1125 plus 6.75 HP. Horizontal reaction at B. Since there are no horizontal loads acting on the earth, now HA is equal to HP is equal to H. So apply this vertical reactions, all vertical reactions is equal to sum of the all vertical reactions is equal to 0. So this is the equation what we get. The reaction at A plus reaction at B is equal to 10 into 15 plus 50 is equal to 200. Now we are going to calculate these both RA and HA and equating, that is equal to 2. It means H is equal to 133.33 kilonewtons after done all the calculations. Now from equation 2, so we are going to substitute this into this and again from here, and we will get this R reaction at A is equal to 65, reaction at B is equal to 135. So after done all the calculations, we will get these reaction forces. Now move on to the bending moment. From inspection, the bending moment, negative bending moment occurs in the region AD and the maximum positive bending moment occurs in the region CB. after understanding these parameters. Now move on to the span AD. Bending moment at any section in the span AD is, so within the x within these limits, so that m is equal to reaction at ax minus h minus 0.03 x square plus 0.6 x. So this with respect to differentiate. So finally x is equal to 1.1748 meters along with the moment minus 14.06 kilonewton meter square we are getting after done these calculations. So for the maximum positive bending moment in the region occurs at D. So moment with respect to D, the bending moment with respect to D is equal to reaction at A multiplied by 5 minus horizontal reaction at A minus 0.03 multiplied by 25 plus 0.6 into 5. So after done all the calculation, we will get this plus 25 kilonewton meter. So this span CB from the figure, whenever this bending moment at any cross section in the span is calculated by the moment. So from locating the position of the bending moment, we are going to consider this differentiation with respect to x, and we are getting this x value, and again substitute this x value into the equation. Finally we will get this bending moment after done all the calculations. So here the maximum positive bending moment occurs at the span CB. Like this, following these are the some of the references which we are going to understand these kind of various problems involved for the parabolic, semicircular, or they are having the symmetric and unsymmetrical conditions also. Like this, first we are going to find out the reactions. After that, as per the given loading conditions, we are identifying the locations and their bending moments, maximum bending moments. These are the some of the references may help enhance the various involve various conditions, few more conditions for identifying the various maximum bending moment using these locations depending upon the various shapes of the arch. So it may be helpful using all these references. And thank you. We will see in our next class.
Like, share and subscribe. Hit the bell icon for more updates.